Good afternoon. My name is Tom Sawinski, and I'm the Federal Program Manager for Fast Reactor Technologies in the Department of Energy's Office of Advanced Reactor Technologies, otherwise known as the ART program. Today I'll be presenting on this year's Fast Reactor Scope, specifically on the experimental investigation of radioisotope retention capability of liquid metal coolants with a focus on sodium and lead. To begin, I first want to go over the ART program's Fast Reactor program's objectives. The overall objective is to develop advanced reactor technology to support demonstration by 2030 and commercial deployment by 2050. To do this, we have several other objectives. The first is to develop scalable advanced fast reactor technologies to reduce cost, improve performance, and increase reliability. We also look to preserve and manage data, knowledge, and experience related to past U.S. DOE fast reactor design, operations, tests, and component technology. We also look to reestablish U.S. infrastructure to support testing of advanced technologies, such as fast reactors. We also look to collaborate internationally to leverage and expand our fast reactor R&D investments. And, very relevant to this year's call, we also look to train the next generation of engineers and scientists by engaging them in advanced fast reactor design and analysis. To meet these objectives, the ART program's Fast Reactor program has prioritized its research and development to address two recurring issues with advanced reactors. The first is to reduce the large capital investment required to develop advanced reactors, and the second is to develop a pathway for non-light water reactor licensing. To achieve cost reductions, we look to apply innovative technology solutions. One area is an improved design approach on components and maintenance for prospective plants. The next is advanced structural materials to reduce both commodities and optimize design. We also look for advanced energy conversion to improve the size and efficiency of fast reactors. Very relevant to the call, we also look for advanced modeling and simulation to optimize performance. We also are looking at fuel development to improve fuel cycle costs. In the area of licensing, we're looking to continue our safety research and development to validate the DOE tools and code suites, and also to look at qualifying fast reactor fuels. I also want to show some insights from the industry-led Fast Reactor Technical Working Group on modeling and simulation. The Industry Fast Reactor Technical Working Group consists of members from the nuclear industry that are focused on developing potential fast reactor concepts. I want to point out specifically that within modeling and simulation, they have pointed out the need for improved source term modeling for fast reactors. The source term refers to the radionuclide release paths during fast reactor transients and design basis events. This is a very important item for the advanced reactor licensing case for fast reactors. By reducing over-conservatism in the mechanistic source term calculation, we can reduce potentially emergency planning zones and emergency planning resources, which can fundamentally reduce operating and planning costs. This graphic shows some of the key areas that are used to develop a mechanistic source term trial calculation. The first is to identify and characterize radionuclide sources. The next is to identify and characterize the potential pathways for these radionuclides. The next is to develop models of the radionuclide transport pathways and their phenomenon. We then look to apply these models and utilize them potentially for regulatory application and review. The Office of Advanced Reactor Technologies has currently supported mechanistic source term work for sodium fast reactors in the form of a trial mechanistic source term calculation. By doing this estimate, we have identified several phenomena related to the source term, as you can see on the slide, such as pool bypass, the fuel release fractions, aerosol deposition and removal, reactor head and containment leak rates, pool vaporization, and noble gas decay chains. From this trial mechanistic source term calculation, we have determined that while a mechanistic source term calculation for sodium fast reactors is currently possible with current tools, to reduce the over-conservatisms that have been developed from these tools, we need to address several gaps which have been identified as part of this trial. And one of these major gaps and areas for improvement is the basis of this particular scope. So with that background, I want to give the background for this scope. So as already described, the Nuclear Regulatory Commission has indicated that the mechanistic source term assessment will be an integral part of their licensing efforts. By improving our best estimate models and tools, the mechanistic source term analysis can provide a more realistic representation of potential off-site consequences associated with transients and design basis events. By reducing the emergency planning zones with better models and estimates, there's a chance to reduce costs. Now, the specific area for this scope deals with the liquid metal cooled reactors and the radionuclide retention characteristics of the coolants. The radioactive retention characteristics may be a mechanism to reduce the off-site consequences within a potential accident scenario. Now you have a bit of a background. I'd like to go the actual FY18 scope. So the scope seeks out experimental programs to provide the data necessary to achieve adequate confidence in sodium and lead-cooled fast reactor mechanistic source term analyses. The specific areas of interest are the data required to properly model the following phenomena for metal-fueled sodium fast reactors and oxide-fueled lead fast reactors. And these areas are the radionuclide interactions with the coolant, the radionuclide behavior within the coolant, vaporization of radionuclides from the coolant, and the transport of radionuclide gas and vapor bubbles through the coolant. I'd like to note that DOE facilities do exist that may be leveraged for a potential experimental program from an applicant. One such example is the Snake sodium loop at Argonne National Laboratory. It's important to note that since the phenomena of interest in this scope are chemical in nature, it's assumed that non-radioactive isotopes can be utilized for the experiments with acceptable results. I would also like to note that it is important for applicants to properly characterize how their experimental program will resolve gaps in the knowledge base while not repeating past efforts already done through the ARP program. To assist with this, 3 reports have been provided on recent DOE fast reactor mechanistic source term efforts. These reports can be found on the screen and are available at the website listed on the slide. And finally, at the bottom, for any other questions you may have on this scope, you may contact myself, the Federal POC Thomas Sawinski, at the information provided, or the Technical POC Chanju Sofu of Argonne National Laboratory. Thank you for your attention, and I now open it up for any questions you may have.
Okay, please submit your questions on the question box on the GoToWebinar application. Tom, what types of non-destructive measurement? Oh, excuse me, that was a question from earlier.
Understood.
Is there interest in the development of intrinsically stable fast reactors?
That's a very broad term. For this particular scope, we're very specific on what we're looking for in terms of radionuclide retention analysis for both sodium or lead fast reactors. That does play overall into inherently safe fast reactors. That's sort of one of the main phenomena for fast reactors and advanced reactors in general is passive safety and inherent safety within the fuel forms themselves. So.
We'll stay on the line for a few more minutes to see if we get any more questions. Do you want all 4 items to be addressed in one proposal?
These are just key areas. They may interplay with each other in terms of the radionuclide retention analysis. If it's possible, it would be beneficial to address all phenomena, but applications will also be looked at that specifically address the specific phenomena as well out of the 4. But they do seem to interplay with each other, so it seems that they would naturally flow together, which is why we've broken them apart.